Hi guys, in this video we will look at indirect alkylation of carbonyl type compounds. Alkylation at the alpha carbon, alpha to a carbonyl. Now previously we saw direct alkylation, or just simple alkylation. We can deprotonate. LDA is a common base. We need a stronger base, then more strong than sodium hydroxide, make anion, and then anion can directly be alkylated as it participates in an SN2 substitution, and we can make this carbon-carbon bond. The alpha carbon has been alkylated. All right, but let's look at an indirect approach using a dummy or activating group. And this will all make more sense once we see what we're talking about. Consider this dicarbonyl compound. Okay? It's a beta keto ester. There's your ester. There's the alpha carbon. The beta carbon is a carbonyl. It's a ketone actually. Beta keto ester. But because we have two carbonyls, the H's, or one of the H's between the two carbonyls, is more acidic than the alpha H's on the left side of the carbonyl. And this is an example of a compound that I can show generically like this. A CH2 group between two electron withdrawing groups. Now a CH3 is called a methyl. A CH2 is called a methylene. Okay? So the methylene hydrogens between the two carbonyls more acidic than the methyl hydrogens that is only alpha to one carbonyl. By the way, a CH is called a methine. Never stated this terminology before. Okay. By the way, CH2Cl2, called dichloromethane, also called methylene chloride. All right, common solvent. This is an activated methylene compound. pKa, all right, here, approximately, let's say 10 to 12, where the H's alpha to just a single ketone would be about 20, so much more acidic. Acidic enough that we can use an oxygen anion base. Okay. These electrons take an H, these electrons stay behind, and we can get this anion plus ethanol, which has a pKa of about 16, which is favored. 12 or 16, weaker acid is favored. We see that the anion this side is favored even when using an oxygen anion as base. Where over here, when we tried to use an oxygen anion as base, the reaction was not favored. All right. Essentially, ultimately, we are using an activating group to make the CH more acidic. And this ester is going to end up being an activating group or dummy group that we will later remove. All right. Now, why are we using ethoxide here? Why didn't we use hydroxide like sodium hydroxide? Well, we've got this ester. This nucleophile, base/nucleophile, could also add to this carbonyl electrons up, eventually back down and kick off that leaving group. But if this attacked and you did that chemistry, you would not get anything new. But if hydroxide did that, we would end up hydrolyzing our ester and getting a carboxylic acid here. So we want to use a base that's consistent with the ester group. So if it did exchange, and it likely does, we don't get anything new here. All right. So complete formation of this anion because we have an activated methylene compound, much more acidic CHs. Now that we made our anion, we can come in here with some type of carbon with the leaving group and do a good old-fashioned SN2, and that would give that product shown there. All right, that product could be isolated. Next reaction, though, is we could take and hydrolyze this ester, okay, aqueous acid, and as we saw during test 3, that should give the carboxylic acid. All right, Ester hydrolysis. You know that mechanism. But with heat, this compound will not be isolated. This is called not a beta keto ester, but a beta keto acid, because this is now a carboxylic acid. And you will see beta keto acids all the time in biochemistry. All right. And beta keto acids will decarboxylate, all right, readily, and lose CO2, especially with heating or with time or maybe in the body, perhaps catalyzed. And if we lose the CO2, basically, we'll look at the mechanism, but the CO2 is lost, and this carbon, which only has one H here, gains an H, and now that carbon has 2. And we end up in this sequence with just a ketone. And that's actually the same compound we made over here, but over here we made it by a direct alkylation of just acetone. Had to use a stronger base. Over here we're making compound A by an indirect route, ultimately an indirect alkylation, starting with a beta keto ester. The ester group is serving as a dummy or activating group to make the H's more acidic, so we can use a less or a weaker base. We do not have to use LDA here. And after we alkylate, we can remove the ester, all right, by hydrolysis to the beta keto acid, and it will usually spontaneously lose CO2. It'll decarboxylate, all right, and we will get just the ketone. Okay, a closer look at the decarboxylation, including mechanism. Probably, if we draw this a little bit differently, All right, it doesn't matter what's here. We'll put the R group. The R group in this case was benzyl. But if we draw this beta keto acid like this, we can do a cyclic transition state. And follow me here. If these electrons take an H, these electrons move in here to make double bond between C and the O. Now carbon is double bonded to two oxygens, and these electrons, okay, move in here to make double bond between C and C, and these electrons move back up to give that oxygen back its second lone pair. And this takes place with heat. This is a decomposition reaction, more specifically called a decarboxylation. We're losing the carboxyl group, we're generating CO2, but this electron movement here should give, okay, double bond between carbon and carbon coming from this arrow. This carbon is no longer bonded to the carbonyl. It is bonded to the R group, and there's also an H there. All right, we have oxygen, but it's single bonded, right? It's two lone pairs, one there, and then the pi bond moved up to become the second. But it's also now bonded to an H, as shown by that arrow there. And the remainder is no longer bonded to this fragment. We have, okay, I'll draw that in as a C. We have double bond to O. That's this. But on the other side, we have double bond to O. And the lone pairs that are there are no different. There's your CO2. Okay. What is this? This is an enol. What will the enol do? It will undergo tautomerization to give double bond will essentially shift between C and the O. There is the product. Okay, we know the mechanism. We can show a mechanism for tautomerization if we're under acidic conditions. Oreo, right? We know enols. Okay, and this is this. The R group is just the benzyl. Okay. So it's a cyclic transition state. All right. In the end, what is the take home here? Carboxyl groups that have a carbonyl beta to them are very prone to being lost as CO2. All right. Now we'll clarify this. Essentially, what's serving as the leaving group here is the enol or enolate. All right. Again, we'll clarify that a little bit later. Homework. What if you just took this compound here and heated it? And by the way, that would just be called a thermolysis reaction. What would be the product? Well, it would be just like above. All right? And make sure we read the take-home message. Biochemical application. This is a beta keto acid. It's called acetoacetic acid. Okay. It is prevalent in biochemistry. Under certain physiological conditions, it is formed more than it should be. And it leads, since it's acidic, it leads to acidosis. But it's often called ketoacidosis because it's got the ketone group and the acid. For example, in diabetics, they produce more acetoacetic acid, and it leads to the condition known as ketoacidosis because it's acidic. All right. Beta keto acids. Now, it could decarboxylate. Things can decarboxylate in the body. It's easier in the lab because we can supply more heat. Of course, heat is going to favor one molecule becoming two as entropy is improved here. Okay. Here's a variation of what was this over here? Well, it's a beta keto ester. It's type synthesis, sometimes called an acetoacetic ester synthesis, because this particular molecule is ethyl acetoacetic ester. It's kind of a mouthful. Main thing, it's a beta keto ester. We can also do very similar chemistry using this diester called Malonic Ester or diethyl malonate. Okay. If we treat this with a base, we would expect to deprotonate here. I'm not going to show that mechanism. These electrons, we can then do an SN2, and that would give that product there. Now when we hydrolyze here, this diester would become the diacid, but it will not survive with the heat. And what we have here is a carboxyl group with a carbonyl beta. And we said here, carboxyl groups that have a carbonyl beta to them are very prone to being lost as CO2. Now in this example, we only had one carboxyl group, and the carbonyl beta was a ketone. Here we have two carboxyl groups. Only one will be decarboxylated. Whichever one you want, it's the same product. All right. But this carboxyl group has a carbonyl beta. We will lose it, and the H will end up here essentially. And that will give that product there. And it's actually a carboxylic acid because the carbonyl group that remains is a carboxylic acid in this case. You don't lose them both because this carboxyl group does not have a carbonyl beta. All right. Essentially, we lose the CO2 and an H ends up here. All right. Now we talked about the mechanism, but if you compare this to where we started, It's kind of twisted there, but right here, our group is the benzyl. It's gone, and there's a new H there. Yes, it proceeds via the enol, and then the enol, the H gets relocated to the carbon. All right. So these are some indirect alkylation type reactions using an ester group as a dummy group. All right. Now, by the way, why does it have to be an ester? Well, if this was a carboxylic acid, the strong base would take the acid proton. So we can't have an acidic proton here, leaving these to be the most acidic H's in the molecule. Those are the ones we want to deprotonate. All right. But when we hydrolyze, we get the acid there, and then it spontaneously decarboxylates. All right. Next reaction, Roman numeral 2. Well, what was Roman numeral 1? We spent a good amount of time doing alpha substitution reactions. All right. Now we're going to move to alpha condensation reactions. And the main reaction here, what we'll begin with, is the aldol condensation reaction. Okay. If you take this ketone here, which is an acetophenone, and treat it with sodium hydroxide catalyst, we can get this product here. Now in this case, it's actually a dimerization, two equivalents. Okay, reacts with itself. All right. Got 8 carbons here, we got 16 carbons here. Let's see what's going on here. Well, with hydroxide, we can deprotonate, right, one of the alpha CHs. Now, of course, this equilibrium is not complete, right? Just like here, it's not complete. The chemistry actually works here, though. It doesn't need to be complete. So what can this carbanion attack? We're not throwing in any carbon with the leaving group. There's nothing else for it to attack other than another molecule of itself. And so we can show another. And what happens here in an aldol condensation reaction is an enolate carbanion of one molecule attacks the carbonyl of another. Electrons up. All right. And that would give, this carbon is now bonded to the carbonyl carbon, electrons up to become minus. We just made this bond, but the other carbonyl carbon had a methyl and a phenyl bonded to it. And that is a simple nucleophilic addition of an enolate carbanion to a carbonyl. Happens to be two of the same molecules. Now here we made this plus water. All right, we've got water present. This point, this can take an H, all right, and go neutral. Take an H from water, that would give try to draw this zigzag a little bit. That would give this OH compound plus hydroxide catalyst reformed. Now this is where the name aldol comes from. Because the OL ending, we have an alcohol. This is the original aldol product. Now this chemistry is often done with an aldehyde. I did it with a ketone here. It's kind of complex. Actually, aldehydes don't work as well. Then you say, well, why does it have aldol? But the ald comes from aldehyde, but the OL comes from the fact that you have an alcohol here. All right. But these aldol products, sometimes they can be isolated, but very often they will dehydrate and they're not isolated. And the mechanism is fairly straightforward. The base takes one of these alpha CHs again, just like it did here, and that would lead to that carbanion plus water. Yeah. Now again, the equilibrium is not favored here, but we can still show some of this being formed. And at this point, we remember, anytime you can make a pi bond and kick off a leaving group, easy to do. And this moves in and kicks off that hydroxide. All right. Is an OH a good leaving group? Not for SN1, SN2, E1, E2. But we're not doing that type of chemistry. We're doing the old chemistry. Anytime you make a pi bond, kick off a leaving group, easy to do. And that will give that product there. Okay. The water that we said is going to be formed was formed here. But we also form here hydroxide again. All right. And hydroxide is the catalyst for making the original aldol product. It's also the catalyst for the, what do we want to call the next step? Dehydration, because from going from here to here, we lose water. If you look at the formula of this compared to that, we have lost an H and an OH. That's H2O. Okay? So the dehydration is also catalyzed by hydroxide. And dehydrations are often called condensation reactions because that water can be condensed out. All right? And overall, this can be called an aldol condensation reaction. That implies that water is lost. Water is only lost when we do the second step. If you just stopped here, you could just call that an aldol reaction, but you would not call it an aldol condensation reaction. Now again, this dehydration will often take place spontaneously, and you often cannot keep it from happening, especially if the alkene you're making is conjugated with something in additional to the carbonyl. And in this case, it's conjugated with the benzene ring as well. And that really drives this to be a favored product and drives the dehydration. Okay. classical. Now this is a symmetrical aldol because two of the same, the product is not symmetrical. That refers to the fact that two of the same molecules reacted. Now we can also do a mixed aldol. It's actually more common, but you must have a reason for selectivity. For example, if you tried to do an aldol reaction between this ketone and this aldehyde, you could theoretically get 4 different products. If this ketone reacted with itself as above, you would get this product as above. But if this enolate here, instead of reacting with another of itself, if it reacted with this aldehyde, you would get a different product. Now the same thing over here. Instead of making enolate alpha to this ketone, we could theoretically make it alpha to this aldehyde. All right? And this enolate could attack itself, or it could attack the ketone. Okay? Need to understand, okay, why 4 possible products, where above there was only 1. For example, this here in the lower right, what reacted with what to give this? All right. Now, by the way, we are making an alpha beta unsaturated carbonyl compound. We actually did that before one other way, by elimination here. Okay? I didn't say it back over here. But an aldol reaction also gives an alpha beta unsaturated carbonyl compound. Now when you see these and you're looking to have made them from a aldol reaction, we are making the alkene. All right? 8 carbons, 8 carbons. And of the alkene, 1 carbon was originally an enolate. All right? Enolate. And the other carbon of the alkene was originally, right here, 1 was the enolate, the other carbon was originally carbonyl. An enolate reacts with a carbonyl. That's how you get this alkene. Now what you need to understand and see is, of the 2 carbons of the alkene, which was originally the enolate and which was originally the carbonyl? The answer is easy. The one next to the remaining carbonyl was the enolate, because enolates are next to carbonyls. Okay? So originally, enolate carbon, and originally the carbonyl. The enolate carbon, of course, next to a carbonyl. So down here, if we separate this into that, and this carbon was originally an enolate, okay, and show enolate or just show it neutral. The other carbon was a carbonyl. Now, there's an H there. Let's draw in the H. That's an aldehyde. And so this product comes from this carbanion attacking here. And if you continue through your mechanism, you will see that this eventually gives that product. This product comes from the enolate of the ketone reacting with the aldehyde, where this product comes from the same enolate but reacting with the carbonyl of another molecule of itself. Think about that for these other two and understand how these are formed. What enolate is reacting with what carbonyl? Okay, so you need to have selectivity, otherwise you're going to get a mixture. Here's a case where you can get good yield, and it will be selective. We can call it regioselective or chemoselective. Chemoselective reaction. And you may recognize that this is a chalcone. All right. We treat this with hydroxide. Where are you going to make enolate? Well, the only place to make enolate is here, because this aldehyde does not have any alpha CHs. And an aldehyde H is not acidic. So only one enolate possible. By the way, only one side of this molecule, because the other side there is no CHs. So that's the only place you can make enolate. Now, this can either react with the aldehyde or another molecule of itself. And the question now becomes, well, which is more reactive carbonyl? Which is more electrophilic, the ketone or the aldehyde? Well, this has a carbon which donates. That makes the carbonyl, okay? sp3 donation decreases the electrophilic character of the carbonyl. Aldehydes are more electrophilic, they're more reactive towards nucleophiles. Doesn't have the other sp3 carbon. The other side is the same. And this could theoretically be some strong electron withdrawing group. Okay. In general, aldehydes are more reactive towards nucleophiles than ketones. And indeed, when this is looking to react, oh yes, it reacts here. And off you go. Aldol, it's going to dehydrate because the alkene is conjugated, in this case, not only with the carbonyl, but also the benzene ring. And chalcones is a mixed aldol, okay? But it is going to be chemoselective. All right. Only one enolate possible. That cuts your number of possible products in half. See, over here we have two enolates that are possible. Form enolate there, but we could also form enolate here. It could react with itself or the aldehyde. It could react with itself or the ketone. Now, we do see that the aldehyde should be the more reactive carbonyl in terms of nucleophile adding to carbonyl. So two of these may be more favored than the other two, but you're still going to have at least two probably major products. Over here you only have one because there's only one place to make enolate. All right. Recall, there's another way to make such products. And we already referred to it right here. We could do an alpha halogenation and then put the double bond in by an elimination. All right? So if you had this molecule, we could put that double bond in, alpha halogenation, and then eliminate. All right? Now, this brings us to intramolecular aldol condensation reactions, where we're going to make a ring. All right. If you take this, let's see, 1, 2, 3, 4, 5, all right. It's a diketone. 1, 2, 3, 4, a 1,5 diketone, it can be called. Treat it with sodium hydroxide, it will end up being a catalyst, we will see. We can get a ring. What size ring, though? Well, let's first show what does happen. We're going to make enolate right here. We can make it here or here. Now it's a symmetrical molecule. If we had showed it here, well, that's the same thing as here. If we had showed it here, that's the same thing as here. Either one is possible. These anions are in equilibrium with each other. But what can happen if we do make enolate here? It could attack here. And that would give what size ring? 1, 2, 3, 4, 5, 6. All right. And if we remember, 5 and 6 membered rings are your best sizes. If we had made enolate here and it attacked carbonyl, that would have been a 1, 2, 3, 4. Not as good of a ring size. The 6-membered ring is favored. This reaction will give all right, let's see if we can draw it. There's 3 carbons between the carbonyls. All right, then the carbonyl, and then another methyl. Why don't we just redraw this like this first? There's the molecule. We had the carbanion here, and it attacked carbonyl electrons onto oxygen. And that gives a 6-membered ring. Carbonyl here. 1, 2, 3. This carbon used to be the carbonyl. Electrons moved on to oxygen, became minus. We made this bond here, but that carbonyl carbon also had a methyl. And so this carbanion just added to carbonyl, electrons up onto oxygen. Simple nucleophilic addition. All right. From here we're going to do the aldol condensation. Look back. Anion. All right. The oxygen takes an H. We get the OH. So eventually this is going to become OH. But then we make enolate again. Same position. Then we expel that OH. Because anytime you can make a pi bond, all right, kick off a leaving group. All right, we made this plus water. Now I could take an H from water, but what if I take an H from that carbon and just do a proton transfer? And that would give OH, double bond, methyl, All right. And I skip this taking an H from water and then hydroxide coming back and taking an H there. What if this just takes an H there? That is perfectly reasonable. Proton transfer. All right. Back over here. What I've done is I just went straight from here. Is this oxygen basically takes an H from here instead of from water. And if we did that, we would get this structure here directly. Enolate with that OH on the beta carbon. Enolate OH on the beta carbon. And now, anytime you make a pi bond, kick off a leaving group. And the product here will be double bond there. And don't forget the methyl group. And here's our alpha beta unsaturated carbonyl compound. All right, we made a 6-membered ring. Not a 4. Because if this had, all right, homework. What would 4-membered ring look like? Because if we had made carbanion here and it had attacked, it would have been a 4-membered ring. All right. So also show the possible 4-membered ring, and then of course between the two, the 6 is favored because 5 and 6 are your best sized rings. What about here? Here we have, what's the difference here? Oh, here we have 4 carbons between the carbonyls. There we only had 3. All right. So for homework, show product there. What ring is going to be formed here by an intramolecular aldol? Because remember, intramolecular reactions are always faster than intermolecular. If it can react internally rather than another molecule, that's going to be faster. All right. Need to be able to go backwards. We talked a little bit about that over here, okay? For homework, show how each of the following can be made using an aldol condensation reaction. Provide the starting materials. All right. What reacts with what to give these products? Now this one is actually going to be a single molecule that reacts intramolecularly. But what does that single molecule look like? Okay, the aldol reaction, very important. We'll end this video there. There's a couple of applications we'll look at. And then we will pick up in the next video with the Claisen condensation reaction. That involves esters. So the aldol typically involves aldehydes and ketone chemistry. All right. We're pushing towards the end of this handout here. Next big topic after the Claisen will be the conjugate or so-called Michael additions of alpha-beta unsaturated compounds. All right.